So there's a couple weird things going on in the table of Laplace transforms. So we're going to take the next couple videos to understand those. So this video will be exclusively about line 12 of the table, and the next video will be about lines 7 through 10. All right, so let's look here at line 12 of this table. You see the Laplace transform is this function, e to the minus cs over s for s greater than 0. Perfectly valid thing to see in a differential equations class. The inverse function, or the function it came from, is this thing called u(c) of t, which we haven't seen before. So let's look at what that is. All right, so what did that table say? That table said if the Laplace transform of a function was e to the minus cs over s for some s greater than 0, then the function is this function which we call u(c) of t. We call this the unit step function. Unit meaning 1, step function meaning there are steps in it. So it's 0 if t is greater than or equal to 0, less than c, and 1 if t is greater than or equal to c. So we're only defining it for non-negative t's. What does the graph of this look like? We're 0 as t goes from 0 to c, not including c. So we have an open circle there, and then we go up to 1, starting at c and continuing on forever. That's the graph of the unit step function. So there's a step, and we end up at 1. Okay, let's make sure we believe this. So we're actually going to calculate the Laplace transform of u(c) of t, even though the table already tells us what it is. That's, by definition, the integral from 0 to infinity u(c) of t e to the negative st dt. Okay, and it's a step function. But it's okay, we know how to integrate step functions from integral calculus. We're going to go from 0 to c, u(c) of t e to the minus st dt, plus the integral from c to infinity, u(c) of t e to the minus st dt. And then what happens to u(c) of t? From 0 to c, it's 0. So this is the integral of 0 dt. Note that the indefinite integral of 0 is a constant, but the definite integral of 0 is 0. So that's 0. Integral under the area under the curve is 0. Plus integral from c to infinity. Well, if t is greater than or equal to c, then uc is 1. So this is really the integral from c to infinity of e to the negative st dt. And this is pretty familiar. So we can just do this again. Let's see. Integral is negative e to the negative st over s, right? Putting in t going from c to infinity. This integral only exists when s is greater than 0, otherwise it diverges. And when s is greater than 0, then as t goes to infinity, this thing goes to 0. And then we're going to subtract a negative, so it's going to be a plus, and we're putting in c for t, so e to the minus cs over s. Okay, so that is just e to the minus cs over s, which is what we said at the beginning. Okay, so we believe this integral, the Laplace transform table was not making stuff up. Note that the step function, the unit step function, is not continuous. And remember that we said L inverse was only unique, guaranteed to be unique for continuous functions. But in this case, L inverse gave us a non-continuous function. So what does that mean? That, in this case, actually means it's not unique, because what we can do is we can just start throwing in random stuff. Like, let's say there's some other number, d, and we just wanted to, like, get rid of that and put it here. Like, let's say the function at d was 2. Now this is some different function. We'll call this g of t. Well, the Laplace transform of g of t is going to be this same integral. We'll have to split it up at d too, technically, but it's a removable discontinuity, so the value will be the same as this one. So this is also equal to the same Laplace transform. And we can do anything we want. We can remove another, like maybe we'll remove this and put it at -1. We can add in as many removable discontinuities as we want without changing the value of the integral. So this Laplace transform is not unique. It's kind of similar. This has come up in other places in math, like arcsine of 1. There are lots of angles whose sine is 1, but we define arcsine of 1 to be pi over 2 by convention, because that's the most convenient thing to pick. So same thing here. In fact, infinitely many functions whose Laplace transform is e to the minus cs over s, but we pick this unit step function because it's the simplest. So by convention, the inverse Laplace transform gives us the unit step function. Okay, now that we have the unit step function, let's see if we can get other step functions in terms of it. So let's say we start at 1 here, and we're going to go, now we're going to stay at 1 up to c, so this is kind of the opposite, and then we'll be at 0 afterwards. Can we write this function in terms of uc of t? Okay, well, let's see. What happens? We start with the function 1, and then we want to fix it after c. And we want a function that leaves the function 1, g of t equals 1, alone up until c, and then moves it down to 0 after c. Well, the function uc of t does that. If we add it on, it leaves every function alone up to c. So, and then normally it would add 1. So what if we like subtract uc of t? Then what happens? That means we've left this function 1 alone up to c, because uc of t is 0, so it doesn't do anything. And then we're subtracting this value of 1 after that, which means we're sending the function from 1 down to 0. So that's exactly what it did. And another way to think about this is this function kind of looks like, without these removable discontinuities added, this function flipped. So we can think of that. G of t, maybe you prefer to think of this as negative uc of t, which would be 0 from here to here, and then negative 1, and then we shift that up 1. That also gets us the same thing. I showed you this one first because this is the logic we'll be using for future functions, such as this one. Let's look at this one that stays at 0 up to 5, goes up to 1 afterwards, stays there up to, actually let's make this open, this closed, this open at 20, and then we're going to go back down to 0. Can we write this as a unit step function? We'll call this g of t. Well, it starts as uc of 5, sorry, u5 of t. Starts at u5 of t. And then it could have gone here forever, except now we need a function that leaves that glorious u5 of t alone up to 20, and then moves it down 1, starting at 20. So we're going to subtract u20 of t. u20 of t is 0 up to 20, so it won't do anything up to here. And then it's 1 after 20, so if we subtract it, it'll move it down 1. Cool. Other functions. Let's do one in stepwise function notation. So let's call this g of t. We'll say it is 2 when t is between 0 and 4. 5 when t is between 4 and 7. We'll leave the bottom one included in. Minus 1 when t is between 7 and 9. And then positive 1 when t is greater than or equal to 9. Can we write this as, in terms of unit step functions? Well, let's go with the same strategy as before, except we don't have a graph now. We're starting at the function 2, g of t equals 2, constant function 2. And then we want to jump up to 5 at 4. So we need a function that leaves the thing alone up until 5, and then jump up. Normally adding u5 of t would jump up 1. We want to jump up 3. So let's just multiply by 3. The 0 part will stay at 0, so that won't affect it. Now we want to leave this alone up to 7, and then jump down to negative 1 from 5. So we have to subtract 6 u7 of t. And we want to leave everything alone up to 9, because we're good so far. And then we want to jump from negative 1 to 1, so that's a jump of 2 at 9. So there we go. Okay, crazier functions. Because right now everything's still horizontal pieces. Well, what if I had this? We'll call this f of t. And then g of t is going to be, we go from 0 to c down at 0. And then we're going to copy f directly over here. So we'll start it here, and it'll look exactly like f there. Call that g of t. What is that? Well, that means g of t is 0 when t is less than c, and it's f of, we're shifting it to the right by c, right? Shifting it to the right by c, so that's f of t minus c, if you remember your transformations, when t is greater than or equal to c. Okay, and then this is a little weird. I'm going to factor out an f of t minus c from everything here. What does that leave? That leaves 0 when t is less than c, and it leaves 1 when t is greater than or equal to c. Check that out. If I redistributed this back into both, I would get this back. But I know what this function is. This is uc of t. So I'm good. Okay, let's be even more complicated. Last one. We're going to stay down at 0 up until 5. And then we're going to slowly go up to 1. We'll take until 10 to do that. And then once we're at 1, we'll stay at 1 after that. Okay, what is this? Well, this is, first of all, we could write this, if we wanted to, in the notation up here. So we're going to go at 0 when t is between 0 and 5. It doesn't matter, but I like to leave this open because I'm going to include 5 in the next interval, and I'm going to leave the 10 open, and I'm going to include 10 in the next interval. Okay, let's do the easy part. G of t is 1 there, and then from here to here, what do we have? We have a slope of 1/5, and it would intersect the y-axis at -1. So this is t over 5 minus 1. Okay, what about in terms of unit step functions? Well, if it were to continue there, then we'd be in this situation, where f is just this, but shifted over here. So we're going to call f of t t over 5. And then this is going to be, we can just use this formula from the previous case. We'll have f of t over, or t minus c, right? So c is 5. T minus 5 over 5 uc of t. u5 of t, right? C is 5. Okay. Where f is t over 5. Sorry, f of, not over 5 yet. Okay. I'm either using f's or I'm not. Here I am. So f of t minus 5, u5 of t. And then what I need to do, I like adding. So I'm gonna find a function to add. I'm going to add this function here, which goes 0 here, and then like this. So I'm going to add, those two will add to 1. Notice that it's pretty much a mirror image. The mirror image would be here. I've shifted it down by 1. That way they add up to 1. Make sure that checks out. Otherwise they're going to add to something bigger. Okay, let's see. What is this function? Well, if I put it here, that would just be negative f of t, right? So I'm going to subtract u10 of t f of, and this is negative f of t shifted over by 10, t minus 10. Check that out. Make sure that works. Okay, so other way of writing this is if you just wrote it without defining f, this is t minus 5 over 5 minus u10 of t, t minus 10 over 5. And we are going to come back to this example at the end of the next video.